This is an example of a flow net where seepage occurs underneath a slope. I'm going to trace the ground surface with the tip of the pen. The ground surface is denoted by these little dots. So we start here, this is flat. Then the ground surface goes up a little bit along this small dam which retains water, then down the slope, and then back to flat again. A few things to say here. The reservoir that is being retained by the dam over here has a small height, let's say, or depth, 0.2 meters. This is why it is referred to as a pantano or swamp. The second thing to say is that over here in the downstream side, there is a structure, estructura futura, which means a future structure. So we're going to ignore that for the example that we're going to solve in just a second. There's also an interesting feature about the water table in this problem. You can see that in the upstream side, where the swamp is, the water table is simply the surface of the swamp, right here. In the downstream side, you can see the water table denoted by the little triangle there, which basically means that the water table is lying essentially at the ground surface, which is on this line right here. Now, in the middle of the slope, or in the middle of the geometry here, where the slope is, you can see that the water table is actually slanted. I'm going to trace it, let's say, with the tip of my pen. So the water table, once it gets into the embankment and then down the slope, you can see that it's slanted, right? It's underneath the slope, and then it actually reaches the surface of the slope and lies on it all the way until the downstream side where it becomes flat again. So that's the water table. And that is denoted here in Spanish, superficie del agua libre, which is basically the water table. So here, they're showing you where the water table is underneath the slope. The last thing to notice here is this graphic here, which basically shows that the head lost is the same when we go from one equipotential line to the next. So that's what they're showing you there. And we know that to be true already, if we know how to operate with flow nets. Now we're going to proceed to do some calculations using this flow net. We are going to calculate the heads at point A and the pressure at point A. What are the heads? The total head, the elevation head, and the pressure head. We know that the velocity of the flow is likely to be very low or small because this is soil. That is, the seepage velocity is likely to be very small, and therefore we can assume that the velocity head is 0. We are also going to calculate the pressure at point A. That is the water pressure. And that means that we need the pressure head, which we are going to calculate. And we just have to multiply that value times the unit weight of water to get the pressure. For calculations, we obviously need dimensions. So we have some dimensions here. We have 0.2 meters of water above the ground surface on the upstream side. The thickness of the profile of soil, that is the soil layer, is 6.3 meters. In the downstream side, the thickness is 3.4 meters, and we have designated the interface between the rock and the soil as the datum, which is the typical assumption or designation that we make. Point A is located 1.7 meters from the datum. So that right there tells us, by the way, that the elevation head is 1.7 meters at point A. This is the easiest parameter to find because it is simply the vertical distance from the datum to the point in question. Pressure head at A, what is it? Well, to get it, we first need the total head at A. First, because the point is inside the flow net. So here we go, total head at A. The first thing to do is to find the head, the total head, at the first equipotential line. What is the first equipotential line? It's the beginning of the flow net, right? Which is this line right here. The ground surface on the upstream side in this case. So what is the total head there? Well, the elevation head is the distance from the datum to it, which is 6.3 meters. So the elevation head at the first equipotential line is 6.3 meters. And the pressure head at the first equipotential line is 0.2 meters. Notice that in this case, we can actually just look at the value, meaning measure it with a ruler, 0.2 meters, because the point, which is any point along the first equipotential, is not inside the flow net. It's just simply on the interface. Therefore, we can just say that the pressure head is just the distance above, 0.2 meters. So the total head at the first equipotential is 6.5 meters, which is the summation of the elevation and pressure head. The second thing to calculate is the total head at the last equipotential. What is the last equipotential, or where is it? It is at the end of the flow net, which is where the water table is here on the ground surface, on the downstream side. So what is the elevation head at the last equipotential? The distance from the datum to the point. Where's the point? Well, any point along this line here, which is the last equipotential line, 3.4 meters. What is the pressure head on the last equipotential line? Well, there's no water above it, right? So it is 0. Unlike here where there's 0.2 meters above it of water, right? So the total head at the last equipotential is 3.4 meters. The head lost by seepage as it goes from the first to the last equipotential, as it flows, it is the difference between 6.5 and 3.4. So remember, we're trying to get the total head at point A. First step, get the head at the first equipotential. Second step, the head at the last equipotential. Third step, we did it right here, determine the change in head, or the head lost due to seepage in total, which is this minus that, 3.1 meters. The fourth step is to determine the number of equipotential drops for the flow net. So to determine the number of equipotential drops, we start at the first equipotential and then we count every time we move from one equipotential, meaning line, to the next. So we start here. Every time we move from one to the next, we say 1, 2, etc., right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 drops. They're like steps from one equipotential line to the next. So this is 10. The fifth step is then to determine the head lost per drop. Head lost per drop. We know that the entire head loss is 3.1 meters. And we have 10 drops. So it's 3.1 meters lost in 10 drops. That's 0.31 meters lost per drop. And so that is to say, if you will, that each of these distances here is 0.31 meters. So what is the head at point A? Okay, well, let's think of it this way. Let's say a water droplet which lies right here on the ground surface, which is the first equipotential line, right? It has 6.5 meters of energy, or head. And every time it reaches an equipotential line, it has lost 0.31 meters. So the droplet starts here with 6.5 meters, and then loses 0.31, 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 and reaches point A. Okay? These are 7 drops. 1, 2, 3, 4, 5, 6, 7. So 7 drops and 0.31 meters lost in each one. That's all that is lost. So we start with 6.5 up here, and we lose 7 times 0.31 by the time we get to, meaning the droplet of water gets to point A. So this is the head at A. Total head, 6.5 meters minus what is lost in terms of head getting there. 4.33 meters. Okay, that's the total head at point A. We know that the elevation head at point A is 1.7 meters. Which means that the pressure head is 4.33 minus 1.7, which is 2.63 meters. Finally, we can calculate the pressure at point A. We use the letter U for pore pressure because the water pressure is the water in the pores, right? At point A. And this is simply the pressure head at A times the unit weight of water, which is 2.63 meters times 9.81 kilonewton per meter cubed, but we can assume that it's 10 kilonewton per meter cubed, right? So this is 26.3 kPa. So elevation head at point A, 1.7 meters. Total head at point A, 4.33 meters. Therefore, the pressure head at point A is 4.33 minus 1.7, and the pressure is the pressure head, 2.63, times the unit weight of water.